All right, section 2.5 deals with continuity. Now, I had mentioned earlier when we first started talking about limits, sometimes the concept of a limit and continuity get confused with each other, and you're going to see why now. Because continuity uses a limit in its definition. So we have two definitions here, an interior point. By the way, continuity is a point-wise definition. I remember that this became a big deal whenever I took my first abstract algebra course and also the introduction to real analysis. When we start looking at doing a lot of proofs in the higher mathematics courses, you need to understand the definition of continuity and know that it applies to a point, not an interval. Although we look at an interval to tell if the function's continuous at a point. An interior point, the continuity at an interior point means that a function y equals f of x is continuous at the interior point if the domain, in its domain, if the limit as x approaches c of f of x is equal to f of c. That means the limit exists and the value of the limit is the same as the function evaluated at that point. The endpoint, you still have the same condition basically. It's just that if you're approaching from the left, now this is the left, you want your function to be defined as the same, the limit to be defined as the function is and be the same value. And you, as you're approaching from the right hand side, you want the limit to be equal to the function evaluated at that point. Now there's two types of discontinuity. Two types of discontinuity. And we've looked at them both, but I haven't called them as such. We have removable and we have non-removable. A removable discontinuity is a point at which you could make the function continuous just by filling in a hole. Okay? A non-removable discontinuity is where you have a jump, where the left-hand limit is not equal to the right-hand limit, and you have a gap that can't be bridged just by plugging in a finger into a hole. Okay? So let's look at a graph here. Identify the intervals over which the graph is continuous. This graph is continuous from, let me use this, -3, and because that's an open circle right here at -3, we have to use an open parentheses, so it's from -3 to -2. And then what type of discontinuity is this? It's a removable discontinuity, because if I slid this point up to fill in that hole, it's just one point there, and I could make the function continuous again. And then it goes from -2 to 0. What type of discontinuity is that at 0? It's removable as well. Are there any non-removable points of discontinuity here? No, they're all removable. There's no jumps. So then we also go from 0 to 2, from 2 to 4, 4 to 5. I'm using interval notation. 5 to 6, and then from 6 to 8. But on 8, I can include that endpoint because there's a dot there. It's not an open hole. And it may not be easy for you to tell unless you're sitting close to the board right now. But remember, continuity is a point-wise definition, and I can include that point because there's not a hole there. Over here, we had a hole, so I could not include that point. Now, this leads to the continuity test. There's these three conditions that have to be met in order for a point to be, or a function to be continuous at a point. This has to be memorized because I believe on your first test I say state the conditions necessary for a function to be continuous. And I'm telling you in advance, so nobody should miss that problem, right? The first thing is the function has to exist at a point. Okay? The function has to exist. Also, the limit has to exist. And then the third thing is the limit must be equal to the function at that point. Okay? You can either write out the symbols or just give me the idea of it. The function has to exist, the limit has to exist as x approaches a point, and then the limit has to be equal to the function evaluated at a point.
So that means that there can't be an open circle.
That's right. Okay. So hopefully you have these written down, because the next example, I'm going to slide this up and you may not be able to see it. So state whether the function graphed is continuous on the interval from -1 to 3, including -1 and 3. If not, where does it fail to be continuous and why? So from -1 to 3, is this function continuous everywhere? And if you're in the back of the room, you may not be able to tell. Why is it not continuous? F of 0 does not exist. 0 is in this interval, and there's an open circle right here where the function is not defined. So there's a point of discontinuity. Is this removable or non-removable? No, it's removable. If it's just a whole, this function would be continuous if that was colored in, right? Yeah, so this is a removable discontinuity.
Why does it not exist right there?
Because there's a hole at the graph in the graph right here. It's hard to see it, but this point right here has a hole on it. Right there. Can you see? The function's not continuous there. See, if I were to draw this right now, I would have to lift my pencil up at that point. The pencil test. That's a good way to tell. If you can trace over the picture and not have to lift your pencil up at all, it's continuous.
I think that's what you said again, they're getting that confused. Continuity.
Yes, continuity with limits. The limit exists here. The limit as x approaches 0 of f of x is equal to 1. The limit exists, so that's all fine, well, and good. The one that fails is this one right here. F of 0 does not exist. The function is undefined at x equals 0. I know that because there's a hole right there. That first condition is the one that exists.
That was a filled-in circle, it would exist?
Yes. And we're going to look at some more, I believe. All right. Next graph. What value should be assigned to f of 2 to make the extended function continuous at x equal 2? Right here, there's an open circle. What value do I need to assign to the function at x equals 2? 1. In order to fill this in, I need to, somewhere in between here, say that the function is equal to 1 if x is equal to 2. Because right here, if I were to fill that point in, then the function would be continuous at that point, right? So, there it is. All right. At what points, if any, is the function given here by y continuous? Oh, wait. Hang on. I thought of another question. How many points of discontinuity are there on this graph?
2.
1, 2, 3, 4. There's 4 points of discontinuity. Yeah, that's open, that's open. Oh, wait, that one's filled. No, it's not. That's open because there's a point up there. That's open, and that's open. So these are all points of discontinuities.
This is at 4 or 5.
You're right. 1, 2, 3, 4. So we have discontinuities at x equals 0, 1, 2, and 3. All of these are removable except for what? Right. It's a non-removable discontinuity at x equals 0. All of the others are removable because all it takes is a point. Stick your finger in the hole and it's continuous, right?
So there's only 4 then.
Yeah, there's only 4 points of discontinuity. I circled both of those endpoints and counted them twice. I shouldn't have. Sorry. Yeah, it's just got a bigger gap. At x, the question was at x equals what? Well, here at x equals 0, at x equals 1, at x equals 2, and at x equals 3, we have points of discontinuity. Those are the only places. Okay, moving on to the next question. I'm sorry, I just saw that graph and I saw a non-removable discontinuity for the first time and I wanted to take advantage of a teachable moment, so I taught. All right, the next question says, at what points is the function continuous? Well, whenever you have a function, we can, if it's a function based on the definition of a function, we're going to say it's continuous everywhere except where it's undefined, right? So a function is going to be continuous everywhere. Relations maybe not, but functions definitely. Any function is continuous everywhere it is defined. So what we need to do is we need to find where this function is not continuous. So we're going to find where the denominator is equal to what? 0. So that's what we're going to do. So we start with the denominator here. We have y equals x plus 6 over x squared minus 8x plus 12. Well, that's going to be y equals x plus 6 over, can we factor the denominator? X minus 2 times x minus 6. That'll work, won't it? So this is going to be undefined at x equals what? And what happens at x equals 2 and x equals 6? We have vertical asymptotes. Do you remember that from college algebra? Whenever the denominator of a rational function is equal to 0 and you don't have any common factors to reduce it, that's where you have your vertical asymptotes. At x equals 2 and x equals 6. Tell me, are those removable or non-removable discontinuities? These are non-removable.
How can you tell that?
Because it's not just a hole in the graph, it's actually an asymptote. Okay? Do you remember how to tell when you have a hole in the graph of a rational function? We have vertical asymptotes when the factors in the denominator don't cancel. With the factors in the numerator, I'm just not going to write that part out. If you can't reduce the fraction, then wherever the denominator is 0, you have vertical asymptotes. You have holes in the graph, and holes, remember, are removable. Vertical asymptotes are non-removable. Holes are removable. And we have holes when the factors in the numerator and denominator cancel. Between the numerator and the denominator. Okay? All right. If we go down then to Theorem 8, this, by the way, is on page 95 of your book. These are the properties of continuous functions. Remember, continuity is a point-wise definition. If the functions f and g are continuous at a point x equals c, then the following combinations are also continuous at x equals c. You can add two continuous functions together and get a continuous function. The difference of two continuous functions is continuous. Constant multiples are continuous. Products are continuous. Quotients, powers, and roots are also continuous. This looks very similar to our definitions of limits or properties of limits. Do you remember that? That's because behind the definition of continuity, we have limits. Remember those three conditions that have to be satisfied. 2 out of the 3 involve limits, right? Continuity and limits are closely related. All right, Theorem 9 says the composite of continuous functions. It says if f is continuous at c and g is continuous at f of c, then the composite g composed with f is also continuous at c. Just more algebra for you. All right, next problem then. We want to define g of 7 for the given function so that it's continuous at x equals 7. All right? So the first thing we want to do here is look at reducing this fraction. Okay, so this is going to be equal to, I have a common factor of 6 I can pull out, don't I? What's 294 divided by 6? 49? Thanks. Over, and if I pull a 6 out of the denominator, I get x minus 7. You with me? So this is going to be equal to x plus 7 times x minus 7 all over x minus 7. So because I have a common factor right here that will cancel, that means that I have a hole in the graph at x equals 7. No, it's where this factor would be equal to 0, and that's going to be 7. Okay? So, here's my function g of x. I want to define a similar function f of x so that I end up with a continuous version of g of x with that hole removed. This function g will be the same as the graph of the function x plus 7, provided that x is not equal to 7. Strike that. I need this. Sorry. It's going to be the same as 6x squared minus 294 over 6x minus 42, provided that x is not equal to 7. The question then becomes, what does this function have to be equal to if indeed x is equal to 7? Well, I go over here and I plug in a 7 in place of x in my reduced form of the function, and I see that I end up with 14. 7 plus 7 is 14. So if I have this piecewise function f, then g of x will be continuous if f of, or g of 7 is equal to 14. Okay?
Where was 7 plus 7?
Right here. After I reduced the common factors, I was left with this. So what that means is I have a hole at 7, and if I replaced x with 7 right here in my remaining factor, that tells me what y has to be when x is 7. Remember, this was the way that we evaluated our limits we reduced the fraction and then used direct substitution to figure out what the limit was. So once we reduce the fraction, I'm looking at then I need this limit as x approaches 7 of this to be defined. I need to know what that is. Well, I go through the process of reducing the fraction, and I say, well, that's going to be the limit as x approaches 7 of x plus 7, because that's what my fraction reduced down to, right? And that limit then is equal to 14. So if g of 7 is 14, then the function is continuous. Yes?
I get the end, it's the first one, the x is not equal to 7.
Uh-huh.
It's that way because if you plug 7 in.
You have a hole.
Oh, okay.
But that hole is going to be right at 14. So what I did was I've defined then, I filled in the hole with a point. When x is 7, y is 14. Okay? All right. Now, this is another one that I like to put on exams. I just think they're fun. All right. Oh, by the way, I didn't fully summarize all of this. What all of this means is that when, looking at all of this, when x is equal to 7, g of 7 should be equal to 14 in order for g to be continuous. Okay? At that point. All right, 48 says for what values of a and b is this continuous, is this function going to be continuous at every point? Well, this is a linear function. This is a quadratic function, and this is a linear function. And we've got to find a and b. And the only place that we might have to worry about discontinuities are when x is equal to 0 and when x is equal to 2. So our possible points of discontinuity occur at x equals 0 and x equals 2. Do you see why I selected 0 and 2? Because on this piecewise function, that's where the domain is broken up, right? In order for this function, when I graph this linear, this quadratic, and this linear function, in order for it to be continuous, this endpoint right here has to match up with this endpoint right here at x equals 0. Does that make sense? Now, because the video didn't see me pointing to the board, what I'm going to say is this endpoint on the linear function has to match up with this endpoint on the quadratic function. So what we're going to say then is at x equals 0, looking at the linear function, we need ax plus 2b to be equal in value to x squared plus 3a minus b. Would you agree with that statement in order for the function to be continuous? Okay. And at x equals 2, we need what then? I agree with that. Okay? So working with this top one up here, when x is 0, what I'm going to get? A times 0 plus 2b equals 0 squared plus 3 times 0 minus b. So when I simplify this, I get 2b equals negative b. So far, so good?
Yeah.
And I got that by plugging in a 0 for x. All right. Oh, 0. A's not 0. My bad. That's going to be 3A. Yeah, that's an A. I plugged in a 0 there, and I shouldn't have. So we end up with 3A minus B here. There we go. Now let's add B to both sides, just playing with algebra. And what we end up with then is 3B equals 3A. So what do we know then? A is equal to B, right? A is equal to B. So now we have to go down here to this problem and see if we can figure some things out. Since A is equal to B, I'm going to replace x with 2 first, and we end up with 2 squared. I don't know why it keeps erasing it. We end up with 2 squared plus 3A minus B equals 3 times 2 minus 5. So this is going to be 4 plus, since A is equal to B, can I make that B and A in combined like terms? So that's going to be 3A minus A is 2A equals 6 minus 5. So we end up with 4 plus 2A equals 1. Subtract 4 from both sides and I get 2A is equal to negative 3. So what is A equal to? Negative 3 halves. And what is B equal to? Negative 3 halves. So therefore we know A is negative 3 halves and B is negative 3 halves. By plugging in the numbers. I'm fond of these problems because I think they make you think about the concept of continuity. When you have a piecewise function, your possible points of discontinuity are going to be at these breaks in the domain. So if you want the graphs to match up, if x is equal to 0, this upper function plus the bottom function has to be the same when x is equal to 0. Plug in the number for x and figure out what you get from there. And likewise, if you want the quadratic and this bottom linear function to match up at x equals 2, you've got to plug in a 2 for x and then simplify. Okay?
So, did we find out if it was continuous?
We forced it to be continuous by letting a equal negative 3 halves and b equal to negative 3 halves. If a and b are equal to those values, then this is a continuous function. Yes. Because the instructions, if you remember, said find the values of a and b. For what values of a and b is this going to be continuous everywhere? We forced it to be continuous. All right, Theorem 11 is the intermediate value theorem. Basically, it's an existence theorem. It says if f is a continuous function on a closed interval and y naught is a value between f of a and f of b, then there has to be a value c somewhere between a and b so that this value exists. F of c is equal to that. So this is just an existence theorem. So right here, c is somewhere between a and b. That's what this says right here. For some c that's in between a and b, there's a value of y between f of a and f of b. Okay? And I don't think we do a whole lot with this theorem right now. So it's in the book at this section, so I just thought I'd mention it.
What does that mean?
When you have a continuous function, and this is a big deal, if f is continuous on this interval, what that means is if there's a value between f of a and f of b for any continuous function, there has to be a value between a and b so that f of that value is going to be equal to that value between f of a and f of b. Okay? F of c is going to be y naught. There has to be some c in between here so that that's true. Okay, that wraps up section